Money, money, money.
Now, I didn't write this. Trust me, I wouldn't have chosen a name like Wanda. I don't want to. Nobody's in. Your mom's not named Wanda. I guess it's a cool name. 5% annual interest. How much money will Wanda have after 7 years? Let's look at that first statement. Wanda puts $5,000 in the savings account that pays 5% annual interest. You guys need to pay attention to the wording here. 5% annual interest. That's once a year. That's simple interest. So for the first part of question 1, you guys are going to be using this formula right here. The amount at any time is equal to, what was little a again? The starting amount. And then it is 1 plus or minus r, but you're not going to use the plus and the minus in the same formula. That doesn't make sense. It's 1 plus the rate if it's increasing. It's 1 minus the rate if the amount is decreasing.
So it would be 5%.
And the rate is, well, the rate is 5%, but you don't use 5% in here. What do you use? 0.05. So this would be the formula you can use. The amount at any time, t, is equal to 5,000. And then your base is 1 plus 0.05 raised to a power of t. That's your model. You can use this model to answer most of these questions. How much money will Wanda have after 7 years?
Wait,
well,
not 1 plus 0.05 or 1t?
1 plus 0.05. How much money is Wanda going to have after 7 years? What do we do with the 7? Put it right up there for t. Yeah. So Wanda puts $5,000 into an account that pays 5% annual interest. How much will she have after 7 years?
You just took that in the calculator?
Mm-hmm. Just a calculator problem.
7,000 divided by 0.5.
Sounds about right. So yeah, it's just a pretty easy calculator problem. Type in your initial amount of 5,000, and then the base is 1.05. And we want to know how much is going to be after 7 years, so put a 7 in there for the exponent. Boom! $7,035.50. Now, the next question in there, how many years will it take for Wanda to double her investment? We've done a question like this way back from the beginning. I think it was lesson 6.1. Remember how it worked? The way that I showed you back then was to graph it, right? So to the calculator. Well, I guess you're already there. To the y equals of your calculator. Now you type in the function, but you're going to leave x as the exponent because you don't know how long it's going to take. If you put a number in there, you're saying it's going to take that number of years. So you've got to leave x as just x. So 5,000. Your base is 1.05 to a power of x. Now before you hit graph, you guys check your window, because remember this graph represents real stuff now. The x and the y-axis represent things. So the x-axis is years, it's time. It doesn't make sense to have negative 10 years, so I'm going to start at 0 years. It took 7 years to grow to $7,000, so we know it's going to take a little more than 7 years to double. Just to be safe, I'm going to put 20. The x-axis represents time. What does the y-axis represent? What is it? Money. Right now I've got negative $10 to $10. Do you think I ought to change that? Probably. She starts with $5,000 minimum deposit, so I'm going to change the Y min to just slightly less than that, 4,000. What do you think I ought to change my Y max to?
A lot more.
A lot more? How much?
8,000?
8,000 wouldn't quite be enough. Because the question is asking how much time is it going to take for her to double her investment. She started with 5,000, doubling would be 10,000, so you at least want to have 10,000. I'm going to put 12,000. Now hit graph. Let's see what this bad boy looks like. Oh boy, I'm getting nothing. Hopefully you've got something.
Yeah, it just said out of window.
Huh. There it is.
How did you get that?
What?
How did you do
What?
spare price? Graph is in this window. Go back to the window. That's 1,200. But bigger than the Y min.
Okay, so we have a nice looking graph. Great. How does that help you solve the equation? Hello. He is here. Josh. Come on now. How does the graph help? Yeah. Yeah, hit trace. See how long it takes you for that Y value to reach 10,000. Ooh, it's almost there. Oh, there it is. $10,023. Now here's the thing though, and I hope I explained this well enough when we were talking about this. This is simple interest. It only happens one time per year. One time per year. On the 14th year, check it out. If I type in x equals 14, on the 14th year she only had $9,899. So does it take her 14 years to get 10,000? No. How many years? 15. You have to use a whole number on simple interest problems. 15 years, she's $10,394. Now, this is a good way to do it. I'm not saying this is a bad way. But now that we know a bit more about logarithms, check it out. You don't even need the graph. If we use this formula right here, she starts with 5,000. We don't know how long it's going to take for it to double, so we leave it as t. But if 5,000 doubles, shouldn't it be 10,000 over here? So 10,000. It's just an equation to solve. You guys solved a few of these on the quiz that you did pretty good on. Right? This is not something that you shouldn't be able to do right now. You should be able to solve this. What are we solving for? How do you solve for something if it's an exponent? You got to cancel the base using a logarithm. But the problem is you have to get this by itself. The 1.05 to the power t has to be out by itself. So that 5,000 is in the way. Guys, dang it. What's the 5,000 doing?
Multiplying.
Multiplying. So divide by it. Divide by 5,000. You get 2 equals 1.05 to the power of t. Truly, this is not any more difficult than any of the questions you had earlier on the quiz. It's exactly the same. And you guys did pretty well on that. How do you cancel the base of 1.05? Use a log 1.05 here and a log of 1.05 there. So on your calculator, if you got the 284, you can use the log base. Beat you. Log base 1.05 up to it's 14.2. Now again, this is simple interest. It can only happen one time per year. 14 flat wasn't enough years. It took 14.2 years, but you've got to go up to the next whole year. So what would you answer here? 15.
Same answer, right? But no graph involved. You just use algebra. And logarithms. Thank you, logarithms, for being so awesome. Is that what you're saying? I knew it was. I was just expressing it for you. So it takes 15 years for that account to develop. But check it out, we're not done yet. Isn't there another part of this question? It takes 15 years to double with simple interest. How long will it take to double if it's compounded continuously? Ooh. Hannah, do you want to shut that door for us? Please. Thank you. This uses a different formula now because it's continuously compounding. Here's a question for you. Do you think it's going to take more time to double or less time to double? Less, because it's continuously compounding, not just once per year. So the formula, and you're going to have to remember this, the formula, the amount at any time is equal to P is the principal investment, that's $5,000. R is the rate, that's 0.05. T obviously is time. Now you have, I guess, the same two choices as you had before. You can take this formula right here, 5,000 e to the 0.05 t, type it into y equals, and just trace along the graph until you get to $10,000. That's not going to be as accurate, though, as using logarithms. Now, she starts at $5,000. After how long will it reach 10,000? That's what the question is essentially asking. So the amount, the future amount, is equal to 10,000. That's what's going to happen if you double 5,000. Well, that's just another relatively easy equation to solve. What are we solving for here? Solve for t again. But guess what? It's an exponent. How do you solve if it's an exponent? Cancel the base. What cancels the e? An ln. Natural log on both sides. As long as you can get this by itself, e to the 0.05t. That's got to be out alone. So divide by 5,000 again. 10,000 divided by 5,000 is 2. So 2 equals e to the 0.05 times t. That pesky t is still an exponent. Damn. Now you use L n on both sides. Natural log cancels the base of the e. Let's see. Oh, I didn't want to erase that. Let's try this again. 2 equals e 0.05 t. ln here, ln here. E and the natural log cancel out. So you got the natural log of 2 equals 0.05. Ooh, we're getting somewhere now. That t isn't an exponent. Turn this into a number. And then what would you do with the 0.05? Divide by it. So let's do this in just one step. Go to your calculator, type in natural log of 2, and then divide that by 0.05. Natural log of 2 divided by 0.05. Now, didn't we say it should take less than 15 years? Is it a lot less? What's that? It's not actually that much less. What did you type in? It's because there's all these. You rounded off to 13.86, so there's still a bit more. Does that make sense? what you could do, if you're interested, you could do it this way. It seems kind of weird, but it'll work. 5,000. The name will be E 25 X. So that's what your graph looked like, right? So rather than typing in 13.86, that was an approximation. You'd have to type in natural log of 2 divided by 0.05. Type that in, it gives you 10,000 exactly. So, but in order to get that, you would have had to solve it by hand anyway. Does that make sense? Now, here's the thing. You don't have to use whole number answers on this. You had to use whole number answers on simple interest because it only happens one time per year. Continuously compounding interest happens all the time. So that means it could happen at 13.86 years. So for that one, you would use the decimal. Cool, huh?
No? You with me on your live? Okay, go to the very last two problems now. 7 and 8. Once he finally steps down, I'll volunteer to play Wolverine. Might as well.
Okay. So questions 7 and 8 deal with what's called exponential growth or decay. Half-lives.
No, I've heard of this before. No, this is not science.
But I say yes. Mathematics is the language of science.
And math is finally took a turn to the dark side.
The dark side.
That math was used for good until now.
The thing that is going to be a little tricky for some of you is there's going to be a few formulas to remember on this exam. I'm not going to provide them for you. You're going to have to remember the continuously compounding formula, the PERT. You're going to have to remember that 1 plus or minus r formula
On the dark side
for
comes
simple interest. And then you're going to have to remember this formula here for exponential growth, the decay situation.
so excited to think I'm going to pass the test for once. Oh.
Now, somebody erased B. A is the initial amount, is what you start with. Whether it's decay, now what I mean by decay would be question 7, because what's happening on question 7?
There said carbon half-life.
It's a half-life, right? So after 5,730 years, what happens to the amount of carbon-14?
Splits in half.
It's cut in half, so it's decaying over time. Let's take a look at, quickly read through number 8. What's happening on question 8? Isn't the counted bacteria growing over time? So that would be exponential growth down. There's growth and decay. Luckily, they both use the exact same formula. The only thing that you change is B. Well, and I guess the initial amount, but the biggest thing you worry about is B. B, what's a good way to explain this? It's, for lack of a better way, it's what's happening to the substance if it's a half-life. B equals 1/2. Because you get half of the substance remaining at each half-life cycle. A half-life is B equals 1/2. If it's doubling, isn't question 8 talking about the bacteria doubles every 4 hours? So then if it's doubling, then B equals 2. Now you got to think about this. Didn't we already talk about exponential growth and decay problems? How can you look at an equation and know that it's decay? If the base is less than 1. So if it's decay, we have to have a base that's less than 1. And in this case, it's 1/2 because it would be a half-life. How do you know if it's growth? More than 1. And if it's doubling, you do 2. That means it's an exponential growth function. So that's one of the decisions you have to make. You're going to be given the initial amount. That's not going to be a hard decision to make. this value of t, that's the amount of time it takes to complete a half-life cycle or to complete a doubling cycle. Yeah, so if you're doing number 7, you put a 5,730 right here. And then you would just leave x as x. If you're doing number 8, you put a 4 right here because it doubles every 4 hours. Or 21 hours, or whatever it is. Oh, it's every 4 hours. Let's just do a quick example that's like number 8. Write this down. Write this down in your notes. Culture bacteria starts 500, doubles every 45 minutes. You'll see that these problems are really not that bad. Culture of bacteria starts with a count of 500. Doubles every 45 minutes.
Wait, no, the language doesn't tell you what to do.
Well,
Why is it wrong?
first part A is create a model. Create a model. All that means is use this function up here and fill in for the things that you don't know. So fill in the initial amount, fill in the b value. If it's doubling, what should be b? B should be 2. And then for t, you're going to put under 45 because it doubles every 45 minutes. So your model should look like this. The amount at any time. Actually, you know what? Not that it's a huge deal, but this is bothering me. Go back up here. Scratch. I'm going to put the t up here. And the x. The x is the amount of time it takes for the half-life to cycle or for the double. Yeah, let's do it like that. And then down here, there should be a t. I think that would make more sense to plug in a time into t and not a time into x. So a of t is 500, base of 2. So my question to you, how many bacteria after 4 hours? What would you use to find the answer to this?
Would this be x?
We're going to plug something into t. Is that what I'm hearing? T. Yeah. And I'm glad you guys brought this up. This is a very, very common mistake. You guys listening? This happens all the time, and it's unfortunate because I warn students about it. What is this in terms of right here, minutes or hours? In terms of minutes. You can't mix hours and minutes together. If you're doubling cycles in terms of minutes, then whatever you plug in has to be in terms of minutes. So 4 isn't any good. It'd be 240 minutes. Yeah? So really all it boils down to is you plug it in 240 divided by 45. You raise 2 to that power, and then you multiply it by 500. It's a very, very easy calculator problem. One thing that I've seen students do that's helpful is just kind of estimate before even doing the problem, just to see if your answer is even in the ballpark. How many doubling periods have happened for approximately in 4 hours? If it doubles every 45 minutes, so 45 minutes, there's 1 doubling cycle. Hour and a half, there's 2 doubling cycles. So in 3 hours, there would be 4 doubling cycles. 4 hours and 45 minutes, that's 5 doubling cycles. You guys following? So it doubles a little more than 5 times in 4 hours. Would you agree? So let's just double it 5 times. Start with 500, double it once again. 1,000, and then 2,000, 4,000, 8,000, 16,000. So what would be a reasonable answer for this problem? More than 16,000? You following? Okay. What do we actually get? Nothing? We get nothing? That's more than 16,000, right? Because we know it doesn't double 6 times, so it's got to be less than 32,000, more than 16,000. So let's read the number. Sounds like somebody have it.
Oh, I got it right.
1,158. Now, remember, this number represents actual bacteria cells. So we got to decide if it would make sense to have decimals.
Don't think it'll work.
It really wouldn't, would it? Because we're counting the number of actual bacteria cells.
So if you have like 0.9, would you just round it up?
You just have to run it down because that 0.9 just hasn't quite made it yet. These guys are still splitting themselves. So we would do 20,158. So we don't really have time to go over number 8, but what's the only difference going to be on number 8? We start with what? 30. How long does it take to double? So instead of a 45 here, you would have
21. Wait, no.
How long does it take to double?
4.
So you have a 4 right here, and then they want to know how long it's going to be after what? 21 hours. So it's the same problem, just a few different numbers. Okay? So that's bacteria that's doubling. Check out number 7. Archaeologists use carbon-14 to date using the half-life. Number 7 is almost identical to number 8 and the one we just did. What are some of the differences going to be, though? Instead of 2, you're going to have... Matter of fact, let's just set up the equation on number 7. So the amount... What's the initial amount of carbon-14 in that problem? Come on, it's in there. 24. What's our base going to be? And then it's T divided by however long it takes to get cut in half. Well, T is how long it's, the denominator here is the half-life cycle. So what is the half-life?
Wait, but you said T was on the bottom.
I know, I think I might have confused you.
Yeah.
Let me go back up here. I had to switch it.
Why?
I want you to leave T as just T. X down here is the time it takes for the half-life or the double. The half-life time or the doubling time always goes on the bottom of this exponent. Okay? So going back to this would be your model. 24 to the T over 5,730, but man, they got tricky on this. 30 millennia. So you're not going to put in a 30 for T, you're going to put in 30,000. So again, not a real difficult question there. Guys think you can handle that one? I want you to turn to the front of your worksheet again. Question 2. Take a look at question 2. 2 and 3, matter of fact. Ooh, more chemistry. You heard about the pH scale?
No,
You really haven't?
I've chosen to excommunicate.
Just measures whether a solution is acidic or basic, right? It's less than 7, it's an acid. If it's greater than 7, it's a base. Well, the pH scale uses logarithms, and it's a really easy scale to use. It's just this formula right here. The pH of a substance is negative log of the H plus, the hydrogen ion concentration. This one actually might be given to you, if I remember right. So just a quick example, kind of like number 2. A substance has H plus, whoa, hold on, of 2 times 10 to the negative 3. Hold on. Let's say that you know for some reason the H plus count for concentration of the substance. 2 times 10 to the negative 3. How do you find its pH? You plug this number into here. Hold on. Tell you that's not that hard. Type in negative, common log, and then type in this number. 2 times 10 raised to the negative 3. Close your parentheses. And there's the pH. 2.7. Really easy. What's that? What about it?
Hey. The 6.4 lesson on yet because I looked a couple times and it wasn't on there.
I haven't yet, no. I think I might have time right now before I have to leave. I should be able to